Theoretical physics is a branch of physics that deals with the development of mathematical models and frameworks to explain and predict the behavior of the physical universe. Theoretical physicists use a variety of mathematical and conceptual tools to construct models and hypotheses that describe the fundamental laws of nature and the behavior of matter and energy at a wide range of scales, from the subatomic to the cosmological. Theoretical physicists often work in collaboration with experimental physicists, who perform experiments to test and validate their theories. Together, theoretical and experimental physicists work to advance our understanding of the fundamental laws of nature and to explore the mysteries of the universe. Without our understanding of the underlying mechanism of the nature, all kinds of today technology would be impossible. For examples, communication networking, global positioning system, GPS, high-performance computer and magnetic resonance imaging. The Institute for Fundamental Study, or IF in short, was officially inaugurated on March 14, 2011 by Naresh University Council as a research center unit. From the first day to the present, IF members are working on the cutting-edge areas of research in theoretical physics to expand the boundaries of our understanding of the fundamental laws of nature, including cosmology, gravity, string theory, quantum information science and mathematical physics. We would like to emphasize that frontier research in theoretical physics is essential for advancing our understanding of the universe and developing new technologies that would benefit not only Thailand but the world society.
Hi, welcome to the IF Colloquium number 23. I'm Nina Dang, the head of the Quantum Information Science Laboratory at the Institute for Fundamental Study, or IF, at Naresuan University in Thailand. So we are a research-focused theoretical physics institute that also teaches and grants master's and Ph.D. degrees. And this series of colloquium talks is also broadcast online on Facebook, for maybe not on Facebook, on YouTube, now on YouTube, to promote public engagement of cutting edge scientific research. So today it's my pleasure to introduce Tanmay Singal. So he got a master's and PhD at the Institute of Mathematical Science in Chennai in India. And after that, he had been to many postdoctoral positions, both like in person and I guess virtually during the pandemic. For example, he has a postdoc position at the National Taiwan University and Fudan University in China, where we first met. And then during the pandemic, he had a position at various places in Poland, in Hungary, and in Taiwan. And then he came back to Poland at Nicholas Copernicus University, and now he is at the Institute for Theoretical Physics at University of Cologne, Germany, in the group of David Gross. And I would say probably maybe it's fair to say that he is interested in various mathematical techniques such as representation theory and statistic random matrix theory, and apply them to quantum information problems. So the stage is yours, Tanmay.
Okay, thanks for having me. Yeah, so thanks for giving me this opportunity to present this work. So how do I make my, is there a way to make my, yeah, fine. So I can navigate this, right? Yeah, I can navigate this. Okay, great. Yeah, thanks, Ninat, for kind introduction and for this opportunity to present this work. So right now, as Ninad said, that right now I am in the University of Cologne, Germany. But this work was completed partially during the pandemic when I was still affiliated with National Taiwan University in Taipei, Taiwan, and subsequently when I joined Nicolaus Copernicus University in Poland. So that is why you see these two affiliations over here. So this work is a joint work with Che Chiang and Yijin Su. Both are master students. Both were master students in National Taiwan University. Yijin later on moved to Chung-Yuan Christian University, and with Insan Kim from Hanyang University in Korea. Shisheng Goen, who is the head of the quantum information group in which I was affiliated with in National Taiwan University, and he's also in the National Center for Theoretical Physics, Taipei, Taiwan, and Minshu Shi, who works in Honhai Quantum Computing Center, which is another name for Foxconn Quantum Computing Center. Right. So yeah. So okay, I will start now. Right, so I'll give a brief outline of the talk. What will we be doing over here? Firstly, I will introduce the Pauli and the Clifford groups on D-dimensional systems. Over here, D is an arbitrary positive integer, right? In introducing the Clifford group, I will have to specify the adjoint action of the Clifford group on the Pauli group, okay? And how the Pauli group and the adjoint action of the Clifford group on the Pauli group may be represented on phase space. Okay. Having introduced the Pauli and the Clifford groups, I will then go to stabilizer codes and how to represent them using check matrices. This is essentially sort of a phase space description, and we will also briefly see why counting these stabilizer codes is of significance. Then we go into what is the simplest stabilizer code there is, and how can we using this phase space description, how can we obtain more complicated codes from the simpler code? There seems to be redundancy in this representation of obtaining more complicated codes from the simpler code, and that redundancy is basically it's basically encapsulated in a certain subgroup of the symplectic group. We will see that. So that forms the basis. That gives you a strategy for counting the stabilizer codes, and then we will briefly see what the counting is, how the counting is done. Okay. So I will first, the first half of this presentation, I will go through it quite slowly because it involves certain technicalities and mathematical intricacies, right? So what is the number system that we're working with? The number system that we're working with is the set of integers modulo d. Okay, so we are interested in when you have set of integers, you have two operations on them. Well, you have addition and multiplication, right? So the set of integers is closed under that. But we will do addition and multiplication modulo d. What does that mean? Well, if d is equal to 6, right, then 4 plus 3, which actually is 7 in integers, that amounts to just 1. And 4 times 5, which is 20 in the set of integers, that amounts to 2. Okay, so this is our number system. And the configuration, so we are interested in a d-dimensional qudit. The configuration space of this d-dimensional qudit is precisely the set of integers modulo d. So that is this set over here. And typically, in physics, we know in statistical mechanics, in classical mechanics, and even in quantum mechanics, we're interested actually in the phase space. The phase space of a system plays a significant role in describing the system. So we're interested in the phase space, which is just ZD, like the twofold Cartesian product of ZD, right? So we think of ZD as a two-dimensional vector space over Z. Actually, there should be ZD. Now, technically speaking, this is not quite correct because, I said that d could be any positive integer. So if d is not a prime number, then technically speaking, you cannot call this to, technically speaking, you don't have a vector space over Z. You have a module over a principal ideal domain commutative ring. I'm also not sure with the technicalities of this, but for now, I will sort of loosely use the phrase a vector space over here. And it turns out that everything works fine. Like we don't run into any problems. So Well, I mean, so this is a vector space. So, you have the standard two operations on a vector space. You can add two vectors, right? That you see over here. And there's also scalar multiplication of a scalar with a vector that is depicted over here. Okay. Right. So let's move on. Now, so I just explained the configuration space and the phase space for a d-dimensional quantum system that we're interested in. Right? Now let's look at certain operators with respect to which this configuration space and phase space requires this kind of phase space description. So we introduce two operators, like a generalized X operator and generalized Z operator. The X operator takes this form. So there is a standard basis with respect to which these X operators are expanded like this, okay, and the Z operators are expanded like this. So you can see that these X operators and Z operators, they mirror the well-known sigma X and sigma Z operators that we know for two-dimensional systems. Over here, omega plays the role of the phase. That is, it is a dth power of, sorry, it's a dth root of unity, okay? And the commutation relation between X and Z are just given by this expression over here. Now, these X and Z, they form a group, okay, which we call as the Pauli group for a single qudit system. So this generalizes the Pauli group for, a two-level system, okay? And you have a phase space description of this group. What I mean by phase space description actually is, it is actually a homomorphism from the Pauli group to the group that you saw in the previous slide. That is, this, it's this object over here. So you can see my mouse scrolling on the screen, right?
No, actually.
Oh. Oh, okay. I thought that you could see my mouse on the screen. Okay, so so the line that you see in the middle of this, the middle of the slide, Z subscript D Cartesian product, I mean the twofold Cartesian product of ZD, that plays the role of a vector space, but you can also just imagine it to be, just a commutative group, right? So I want to draw a homomorphism from the Pauli group to this phase space object, which is also just a group. Okay, so how do you do that? Well, the phase, so in the fourth line of the slide, you have that, you map the X operator, which is a generator of the Pauli group, to this two tuple, which is 1, 0, and Z is mapped to 0, minus 1. It should be 0, 1, not 0, minus 1. Sorry about that. Right, it should be mapped to 0, 1. So if you take, a u-fold product of the X operator with itself, so that becomes X power u, the uth power of X, that is mapped to the number u multiplied with the vector 1, 0, and that gives you u0. Okay, so you can similarly do other operations. I mean, so you can, so what ultimately this ultimately the homomorphism that underpins this, all of this, is that the multiplication of operators, the X and Z operators, which generate your single qudit Pauli group, their homomorphic images, the operation that you would do in the image, the homomorphic image is addition in phase space. Okay, so that is well described by the third line from the bottom. Okay, so you see multiplication of two generic elements of the single qudit Pauli group. Okay, and what their homomorphic images, what happens to the homomorphic images when you perform the corresponding operation on phase space. So multiplication of operators on that amounts to the addition of the corresponding images. Okay, so this is the description of a single qudit Pauli group. Okay, now I will move on to the next slide. I will introduce the Clifford group now. So what is a Clifford group? Once I have described the Pauli group, what is a Clifford group? Well, simply the Clifford group is a normalizer of the Pauli group in the set of d by d unitaries. What does that mean? Well, consider an arbitrary Pauli, G. Okay, so G is an arbitrary Pauli. Now, if you were to take an arbitrary unitary from the unitary group, a d by d unitary, and suppose you were to conjugate this Pauli G by this unitary U. So you form the product UGU dagger, right? You would get some arbitrary other unitary. Okay, UGU dagger will be some arbitrary unitary. It will not necessarily belong to the Pauli group itself. But now here's what I do. Instead of taking an arbitrary unitary U, what I do is I take some specific unitaries, okay, some very specific special unitaries, such that no matter what G I started with, UGU dagger will always be a Pauli. So G is a Pauli for any choice of Pauli, and UGU dagger is also a Pauli. I take the collection of all such U's, and it turns out that the collection of all such U's is a group. That is easy to show. Okay. For example, when the dimension D is equal to 2, then two well-known elements of the Clifford group are Hadamard and the phase. Okay. So, in fact, the Hadamard and the phase, they generate the Clifford group for dimension 2. Okay. Now, I gave a phase space description of the Pauli group in terms of vectors. So, elements of the Pauli group, they become vectors on your phase space. Now, the action of the Clifford of the Pauli group is to change one Pauli to another Pauli, right? So that would imply that the corresponding action, the corresponding representation of the action of the Clifford group, but when you look at it on phase space, that amounts to vectors being mapped to other vectors. So, but how does that work out? Well, it turns out that this works as follows. So, for every unitary in your Pauli group, the corresponding transformation that you see on phase space is a symplectic matrix. It's a 2x2 symplectic matrix. Okay. Right. So we will denote the symplectic matrices by the symbol big S. Okay. The condition for a matrix to be a symplectic matrix is given at the bottom of the screen. So you can read it off at the bottom over here. Right, next. Okay, so I gave you a description of the single qubit Pauli group and its phase space description. I also introduced the single qubit Clifford group and its corresponding phase space description. Now we will go to the actual system of interest. We are not interested in just a single qudit system. We're interested in a collection of n qudit systems, right? So you have n different qudits. Okay, each has their own Hilbert space, and we are interested in the joint system. So how do you go about doing that? Well, in quantum mechanics, you go about doing that by taking a tensor product of the individual Hilbert spaces. What ends up happening is that the space of operators that acts on this Hilbert space is also the tensor product of the operator spaces of the individual subsystems, right? So we're interested in the n qudit Pauli group, and the n qudit Pauli group is just a tensor product of the individual Pauli groups on each individual qudits. Okay, you can label an arbitrary Pauli by the second equation on the screen. Okay, so the generators of this n qudit Pauli group are just given by the x and z generators for each individual qudits. So these are labeled by x1, x2, xn, z1, z2, zn. Okay, and an arbitrary Pauli in this n qudit Pauli group will just be a product of these operators. Okay, the phase space description of an arbitrary Pauli, okay, that is G of A, it will be given by this vector A. Now, what is this vector A? Well, if you see the second equation on the screen, you see the x1s and the xi's and zi's, they're raised to certain powers. Okay, so the power is AI. So what you do is you take a collection of these powers into a 2n tuple, and you call that boldface A or just A. So that vector would correspond to the phase space description of this Pauli G of A. Okay. The commutation relations, they're not difficult to decipher. So the commutation, so I mean, if in X and Z, like they lie on the same qudit, then they would have a non-trivial commutation relation. And if they're on two different qudits, then they would commute through each other. So that commutation relation is encapsulated by this matrix lambda. Now, lambda, if you notice, is also the matrix with respect to which you define the symplectic group. So this is where the symplectic group actually comes into the picture. Okay, so just bear that in mind for the next slide. And yeah, so then just like you define the n-qudit Pauli group, okay, sorry, the single qudit Clifford group, you can also define the n-qudit Pauli group in a similar fashion. The n-qudit Clifford group is just the normalizer of the n-qudit Pauli group in the space of all d power n by d power n unitaries, right? So you take any Pauli element and you conjugate it by these Clifford elements, you will get back another Pauli. The phase space description of the action of this Clifford group is then given by these symplectic matrices, which are 2n by 2n matrices. Yeah. Okay, so this describes the system of interest. I'll move on to the next slide. Any questions so far? Okay, I'll then move on. Now, what is a stabilizer code? So the system that we have is an n-qudit system. Okay, so the Hilbert space is isomorphic to, a d power n dimensional complex Hilbert space, right? So we are interested in a k-qudit coding space. What does that mean? Well, it is d power k dimensional subspace of this Hilbert space, but with certain additional, but it is specified using the Pauli group. How is that done? Well, you first define a stabilizer group. What is a stabilizer group? Well, you have a Pauli group, okay, on this n-qudit system, and what you do is you select some Paulis, say g of a1, g of a2, so on and so forth. There are n minus k g, like some g's that you select. Each of these commute with each other. Okay, the phase space description of this commutation relation is just the fact that the symplectic inner product between the vectors ai and aj, that is 0. Okay, so that is the first condition between these among these Paulis. The second condition among these Paulis is that they are all linearly independent. Now, the g's, they generate a group of order d power n minus k. Okay, an equivalent way of stating that is that if you were to take the AIs instead of the GIs, they're homomorphic images on the phase space, then you find that all these AIs of the generators, they are all linearly independent. Okay, the group that these G's generate, that is called a stabilizer group. Now, where does the k-dimensional stabilizer code come from? The stabilizer code is just the intersection of the +1 eigenspaces of all these generators, G of A1, G of A2, so on and so forth. Now, does that even make sense? Well, yeah, it does. Why? Well, first of all, you see the fact that these G's, all of them they all commute. So they all commute. So it makes sense to talk about, their common eigenspaces, right? Also, first of all, these G's are all unitaries, so they can be diagonalized in the very first place. They're normal operators, so they can be diagonalized, okay? And their eigenspaces are all orthogonal to each other, okay? And on top of that, they all commute, so you can talk about common eigenspaces. And the fact that these G's, they generate a group of order d power n minus k, that includes the information that these G's will have they will have an eigenspace of eigenvalue whose value is +1. All of the G's will have eigenvalues +1, right? So you can then talk about taking the intersection of these +1 eigenvalue spaces, +1 eigenspaces of all these generators. That forms the stabilizer code. And you can work out the details, and you can find out that the dimension of this stabilizer code is d power k. Okay, so it resembles a system of k qudits. So that is why you say that's a k qudit stabilizer code. Now, this is the object that we're interested in. We're interested in objects like k-dimensional stabilizer codes. Okay, the thing is that instead of identifying the stabilizer codes, by I mean, how do you identify a subspace, or yeah, how do you identify a subspace? Well, you identify it by a basis, right? But what is the dimension of this basis? What is the dimension of this space? The dimension of the space is d power k. So what you would have to do is you'd have to sit down and write down a basis, of d power k elements. Now that is going to be quite a tough task if k is, I don't know, if k is like, if d is even 6 and if k is, I don't know, 50, it becomes a humongous task to write down. I don't even know if you could actually write it down that easily for these values. A better thing to do is try to identify a simpler compressed form of representing these things. So what you do is you identify these coding spaces using, just the phase space representatives of the generators. So the vectors a1, a2 dot dot a subscript n minus k. Okay, and remember that the conditions on these vectors is that their symplectic inner products are 0, okay, and that they are all linearly independent. So these 2 points need to be like taken into consideration for what follows next. Okay. Okay, so I'll move on to the next slide. Now, in quantum error correction, you're typically interested in these stabilizer codes. You come up with stabilizer codes with very cool properties, right? And many times those cool properties can be extracted out just from the vectors a1, a2 dot dot a subscript n minus k, right? So for that, what you do is you just find a way of representing these codes using these vectors. And how do you do that? Well, I just introduced a stabilizer, a qudit stabilizer code using these vectors. So what you do is you just take these vectors and then you just embed them into a matrix of size 2n by n minus k. So there are 2n rows and n minus k columns. Additionally, in equation 1, as you can see, I mean, the point is that these vectors need to be, they have additional constraints on them. That is the constraints that, their symplectic inner product of any two distinct vectors has to be 0. Okay, so that is encapsulated in this equation h transpose lambda h is equal to 0. Okay, and secondly, okay, one thing I did not write down over here is that the rank of this matrix, that should be n minus k. Okay, so just as I said before, just reminding you again, just as I said before, over here d is not a prime number. So strictly speaking, you may wonder, how can you talk about things like rank, etc., etc., when you're not dealing with the vector space over a field and blah blah blah. Turns out that it all works out. So it was a bit non-trivial to figure this out, but it all works out at the end. So right. So this matrix H is what I will call the check matrix of the code. Okay. Right. Now we are, okay, now this slide states the result. Okay. So we are interested in the number of different stabilizer codes. Okay. What do I mean by that? Well, what I mean by that is that if I were to fix, so what is fixed over here is the total size of the system. So we are dealing with an n qudit system. Okay. And we are interested, let's say, in all possible k qudit stabilizer codes. Okay. So that gives rise to this notion of like, the number of such k qudit stabilizer codes within an n qudit system. So we denote that by the symbol that you see in the first line, the rightmost part of the first line. Okay. So the main result of our work is computing the number of these stabilizer codes. Okay, so in this block that you see in the center of the screen, so we first compute the number of stabilizer codes for an arbitrary value of k, where k is less than equal to n, and we also then compute the number of stabilizer states. Now, stabilizer states occur in this situation where the value of k is just equal to 0. Okay, so you can see that in the top expression, if you set the value of k is equal to 0, you get the bottom expression. Okay, so the number of stabilizer states is often more important than the number of stabilizer codes, although the number of stabilizer codes may also play some role in certain situations. Okay, now I'll go to the next slide. So I introduced some of the basic stuff. Okay, so I introduced the groups that are involved. I introduced stabilizer codes, and subsequently I also introduced the main result. Now, first things first, I feel an obligation to tell you why anybody would be interested in counting these stabilizer codes. Why would anybody care? Well, the numbers of stabilizer, so the number of stabilizer states, which is stabilizer codes for which k is equal to 0, okay, that plays an important role in many different applications in quantum computing and information theory. Actually, I think mostly computing. So for instance, there are many, like, so often one is interested in the convex optimization over what is known as the stabilizer polytope. Okay, so you are often interested in, you have some convex function and you want to optimize that over this polytope. And because it's a convex function, the optimal value is often found, is not often, sorry, it's found at some extremal point of the stabilizer polytope. So to know how the extremal points of the stabilized polytope, how that scales with the dimension and with n, and that is an important task, right? So that is one reason why people are interested in the number of stabilizer states. Okay, and then if you're interested, let's say, in the simulation of stabilizer only operations, then you need to know how many bits do I set aside to represent these the corresponding stabilizer state. Okay. The number was also used in like design theory by David Gross and by Richard Kuhn, like in their paper in 2015, where they proved that the qubit, what do they prove? They prove that stabilizer states form a tree design. They form the stabilizer states form a projective tree design. There, they also used this particular quantity, and it is also used for other results. Yeah. So this is a quantity of interest. It is not a quantity that I'm just we decided to compute just for the heck of it. It is definitely a quantity of interest. Okay, great. So I have explained I've given the main result, what we're interested in, and I've talked about why that would be interesting as well. Now let's go back to, what about earlier work on the same topic? Well, for the case where the D is a prime number, okay, actually not just when D is prime, also when the underlying number system is, so D is a prime power, but the underlying configuration space is that of a field, not of not for z modulo D, where D is a prime power, not for that kind of a number system. David Gross, he computed the total number of stabilizer codes. Okay, and how did he do that? Well, it was a very simple method to do it. Well, you just count the total number of distinct n minus k dimensional isotropic subspaces. Okay, and what you need to do for this what the mathematics, the technology that you need for this proof is just linear algebra. In particular, you just need the rank nullity theorem for this. That's all, nothing else. Okay. But as I mentioned twice earlier in this talk, when D is not a prime, you don't quite have linear algebra at your disposal, because the objects that you're working with, they actually don't form vector spaces, and they don't obey all the rules of vector space. So the notion of linear independence, dependence, all of that is not as simple as the case when D actually is a prime. Okay, so Gross's original proof cannot be used to compute the number of these stabilizer codes when D is a composite number. So what do you do in that case? Well, you have to devise a new method for that. And the new method that becomes a bit more elaborate. For instance, in the previous slide, I just mentioned that you need to count the number of, like for Gross's proof involved just counting the number of n minus k dimensional uh, isotropic subspaces. Okay, that is a proof that you can condense into a small. You can condense that into like a proof of, like, if I'm generous, I can say 10 or 20 lines using just linear algebra. Okay, um, that becomes a lot more elaborate when D is not a prime. So what do we need to do? We use a new technique, proof technique. So just as I introduced the notion of, so I mentioned that a stabilizer code can be represented as a matrix. Okay, so a stabilizer code has generators, and generators can be associated to certain, like each Pauli can be represented as a vector in phase space. Now you take the generators of your stabilizer code. Okay, there are n minus k of them. You take their phase space images. These are the two n tuples a1 a2 dot a subscript n minus k, and you put them inside a matrix, and this matrix satisfies this equation H transpose lambda H is equal to lambda. Sorry, actually it should be H transpose lambda H should be 0. This is a typo. Okay, and H is also of rank n minus k. So now this H, instead of just working with the check matrix X, what you can do is you can embed H into a larger symplectic matrix. So what does this larger symplectic matrix look like? Well, I'll represent this larger symplectic matrix by M subscript big S, okay? And it will have 4 blocks which are delineated along the columns. So the first column is E, then you have L of X, then you have H, then L of Z. Okay, and this is a symplectic matrix. So what you need is that this matrix M subscript S, it should satisfy this equation on the third line. So ms transpose lambda ms is equal to lambda. Now, it is the fact that you can do this is easily provable for the case when D is a prime. Okay, because you can use the rank nullity theorem. Now, the biggest obstacle that you find, okay, so just like I mentioned in the last slide, like Gross's proof involved the technology that Gross's proof relies on is just linear algebra, and in that mostly you end up using only the rank nullity theorem. So because we don't have a field now anymore, and we don't actually have the rank nullity theorem, that is the biggest obstacle that we face. Okay, but the fact that this is always possible, you can prove that using the rank nullity theorem, but because we don't have the rank nullity theorem immediately at our disposal, that becomes a big stumbling block. But we end up proving that some arguments which are similar to the rank, which run in the same spirit as the rank nullity theorem, also hold for this case. So you can always take a check matrix which corresponds to a k qudit stabilizer poles, and you can always embed that into a larger symplectic matrix. Okay, now you can represent this code using so instead of representing the code by a check matrix, okay, we now represent the same code by a symplectic matrix. Okay, but the thing is that the way to represent this code by a symplectic matrix subsumes a lot of redundancy. For instance, suppose ms is one choice of such a symplectic matrix which encapsulate this stabilizer code. Okay, and suppose m prime of s is another such symplectic matrix which encapsulates this stabilizer code. Both of them are symplectic matrices, and both of them belong to a group. This implies that there should be some matrix M such that this equation that you see over here, right above this, the equation that you see in the second last line, that also holds. So what is written over here is just m prime of s is equal to m of s multiplied by some matrix M. Okay, so now this equation has to be true, and also what's more the case that M has to be symplectic. That is because set of symplectic matrices form a group, and m prime of s and m of s, both of them are in the symplectic group, so M should also be in the symplectic group. And what's more, M has this form that is given in the bottommost line. And it turns out that all M's which are of the form, in the bottommost line of the previous slide, I've written them down over here in the first line over here. All of them, if you take them all together, all such M's, they also form a group. In particular, they form a subgroup of the stabilizer group. Okay, so we call this group, let me just call it the T group. Okay, so I've identified the redundancy of representing a stabilizer code with, the symplectic matrices with like by a group. That is a T group. Any questions so far?
Sorry, what are the matrices E and L sub X, L sub Z in the previous slide that you
Okay,
used
let
to
me go.
form? Yeah.
Okay, so what are the matrices E and Lx? Okay, so um, first of all, like you have a stabilizer code, and hence you have the corresponding check matrix H. So that is fixed, right? Now consider this following exercise. Consider this sort of mathematical task. I want to fill in the remaining elements. That is, I want to fill in E, L of X, and L of Z. Okay, these are also blocks of matrices, such that this entire matrix M of S that satisfies the symplectic equation. Okay, so question is there, can one make an assignment to matrix elements in E, L of X, and L of Z such that the symplectic equation can be satisfied? And the answer to that is yes. So E, Lx, and Lz, they, basically they are the other blocks that will give rise to a symplectic matrix. And what are they? I mean, what kind of roles do they play? Well, okay, so if you consider, so I mean, like in terms of, in the language of quantum error correcting codes, Lx and Lz, they will form the phase space vector representatives of the logical X and the logical Z that act on the stabilizer code, which is described by this H. And E, they correspond to like the pure, E basically, it is another abelian. I mean, if you look at the, sorry, E comprises of columns, each of which is a representative of a Pauli group member, which are correctable errors to the stabilizer code. So if any error occurring to a column in E occurs, or a product of elements in E occurs, then that corresponds to a correctable error, which you can, using your syndrome method extraction, you can correct that.
I see. And these are really they are really like you arrange them as columns, right? They're not like like a big matrix with 2 by 2 like number of blocks.
So H, yeah. So I mean, so H itself is a matrix of size 2n by n minus k. Okay. So all other, so Lx will have to be, okay, so Lz would have to be a matrix of size 2n, so 2n rows and k columns. Okay. E will have to be a matrix of 2n by n minus k, and Lx also has to be 2n by k. Right.
Okay. Yeah. Thank you.
Okay. Cheers. So I'll carry on. So where were we? Yeah. So we noted the fact that the representation of any stabilizer code with with a symplectic matrix has redundancy built into it, and this redundancy is encapsulated by a subgroup of the symplectic group that we just denote by T. Now, so yeah, so this is okay. So I just summarized, right? Now it turns out that, so if you think about it, you have a subgroup of the symplectic group. Okay. Now consider any left coset of the symplectic group. Any element, any distinct left coset would have to correspond to a distinct k-qudit stabilizer code. Right? What does this tell you? This tells you that the total number of k-qudit stabilizer codes is equal to the total number of is equal to the total number of left cosets. So it's, which is equal to just the ratio of the symplectic group divided by this subgroup, this T subgroup. Okay, so to count the number of stabilizer, this k-qudit stabilizer codes, all we need to do is, just compute the cardinality of the symplectic group and the cardinality of this subgroup, this T subgroup. But how do you do that? Well, again, for the case where D is a prime, you can use counting arguments to find out the value, find out the size of the stabilizer group, and find out the size of the T subgroup. Obviously, of course, you would do that if you did not have conventional methods of counting the number of stabilizer codes. But as I just mentioned, all you need to do is count the number of n minus k isotropic subspaces, which is precisely what Gross did in his work in 2006. So you don't have to actually go to this elaborate method of computing the ratio of the symplectic group and this T subgroup. In our case, we don't have that luxury. Okay, so we actually have a much harder time in trying to figure out how do you compute this. But let's first consider the case when D is actually, so it turns out that there actually is a trick that you may use. That is, what you do is you compute this ratio for the case when D is actually the power of some prime. Okay, and then what you do is you use what is known as the Chinese remainder theorem to, find out. Then you use the Chinese remainder theorem. So what does the Chinese remainder theorem say? The Chinese remainder theorem says that if D is the product of, if D has this kind of product where, D is, you see this expression on the third line over here. So D can be, this has this kind of prime decomposition, but M1 is the power of the first prime, M2 is the power of the second prime, so on and so forth. Then the number system that we're using, that is Z modulo D, that for multiplication as well as for addition is isomorphic to the Cartesian product of Z modulo, the first expression that you have, that is P1 power M1 times Z modulo P2 power M2, so on and so forth. Okay, so this is the Chinese remainder theorem. At least this is one of the formulations of the Chinese remainder theorem. Now, what does this imply? This implies that the symplectic group, the set of 2n by 2n matrices over ZD, that is nothing but an isomorphism of the symplectic group over the symplectic group of 2n by 2n matrices over the first prime, P1 power M1, and so on and so forth. And this is also true for this T subgroup. And if you remember, we are interested in computing the ratios of the symplectic group and this T subgroup. So what we need to do is we need to compute the ratios of the symplectic group for the first number, that is P1 power M1, by the cardinality of this T subgroup over the number system Z subscript P1 power M1, and do that for all the remaining numbers as well. And we obtain when we obtain like the individual cardinalities for the individual numbers, you can just take the products and that gives you the total cardinality. Right? So that is what we need to do. So because we have the Chinese remainder theorem, what we can do is we can first choose D to be some prime power, so P power M, and we just compute the cardinalities of the symplectic group and this T subgroup for this purpose. Now, the cardinality of the symplectic group can be computed using certain methods, which I found from Math Stack Exchange. So there were some pretty cool methods which one could use for that purpose. But for this T subgroup, one had to use a more clever strategy because it was not so obvious. So what we do is we find a decomposition of this of this T, for any certain decomposition of it. Okay, so any element M can be written as a product of 4 elements. Okay, so MT, ME, MS, and ML. Okay, and this decomposition is unique. There is no redundancy in this decomposition, right? So, and each individual element, you can so each of these individual elements, MT, ME, MS, and ML, they have a certain, so these themselves come from various subgroups of this T subgroup. So you have 4 subgroups of the T subgroup, okay, and you have this very neat decomposition. So what you need to do is, an arbitrary element M of this T subgroup, what you need to do is you need to take individual elements of the subgroups and multiply them in this order, and you'll get distinct elements of M. And you can, this is a unique decomposition. So what you need to do is you just need to compute the total number of elements in each subgroup, and you're done. The only element that, so all of these subgroups, the intersection of all of these subgroups is just the identity element. There is no other element that lies in the intersection of between any of these subgroups. So it's a very neat decomposition that we may use, and you obtain that. Yeah, so actually, yeah, so I verbally gave the entire description of everything when I was hovering over the previous slide. So, like I said, any element M has this decomposition into these subgroups, and all of these subgroups are, the only intersection between these subgroups is the identity elements, and you have a very neat, unique decomposition. So it also turns out that some of these subgroups, they are just like isomorphic to well-known classical groups in group theory. So ML is just a symplectic group, and MS is just the general linear group. Okay, so it is easy to compute the cardinalities of all of these subgroups. And finally, when we put all things together, we find that we compute the total the cardinality of the subgroup, and then we take the ratio. Okay, and when we put everything together, we get a very large expression that you see in equation 2. So for the purpose of this talk, you don't actually have to worry about what this expression means, what Gaussian coefficients are. I just put them in case somebody may have, somebody recognizes these things and they get excited about it and they would like to ask questions about it. But yeah, so there is some expression that you get. The thing is, like, now what you do is, okay, one I did not mention is that once you get an expression for this stabilizer codes over, when D is some power of a prime P power M, what you then do is you use that expression to, like I said in the previous case, I need to go back to the previous slide. Yeah, then you go back to this. Okay, so in this slide, if you look at the bottom expression, what we do is on the right-hand side, we have, for each of these, for each power of a prime that occurs in the decomposition of D, we have obtained the number of stabilizer codes. Okay, so we have obtained each of these individual numbers. What you then just need to do is you just need to multiply all the numbers with each other. Okay, so compute it for the first, second, and for the rth case, take their products, and you finally get the total number of stabilizer codes. And, and that is the number that is given over here. So you get some number, okay, and what you find is that, so the number itself is quite complicated. So, just like you can see in equation 2 and equation 3, the number for the individual case when D is a power of prime itself is quite complicated. But the point is you can find very cute upper and lower bounds. So a lower bound can be given in the form of, the left-hand side expression that you see over here on the last line. And you can find an upper bound on the right-hand side expression that you see on here as well, where the constant C, that is just some number as 2.16. Now, the interesting aspect of this is that if you were to look at the values that David Gross computed, okay, in 2006 using this much simpler method, okay, that is afforded by ZD being a field, you find that his the order of magnitude, the scaling of the number of stabilizer codes, k-qudit stabilizer codes, that scales very similarly to the case when D is not a prime. So the scaling, the power law of the behavior of how this object scales, that is sort of independent of whether whether D is prime or not. But the methods that we need to compute these upper and lower bounds, that is more difficult. So that is what I found an interesting aspect. So you get a similar scaling behavior, but using more complicated methods. Yeah, so our objective has been met, and we have sort of done what we set out to do, and that finishes the short description of this work. Thank you for your attention.
Nice. So the formula is still doubly exponential in n. Yeah. Similar
Yeah.
with the prime case.
I mean, so it goes as d power n squared, or
yeah. So actually, I don't know if the audience here have questions, but I have a few straightforward questions. Maybe first one, in the first time you present the formula for this number of codes. Actually, can you show? Yeah, can you go to the maybe first few slides in which you tease us with the results first, and you have like the general formula and then the formula for the state, for the stabilizer state, right? Number of stabilizer state.
Okay, just give me a second. I'll have to navigate. Okay, maybe I'll just have to go at it slide by slide. Right here.
Yeah, this one. Right. So plugging in k equals 0 doesn't give the last formula. And so I look up your paper, and in the paper you actually state 3 different formulas, and that one you say is for stabilizer code, and then there's another one that's slightly different in the exponent that you say for stabilizer code spaces.
Right. Okay. Yeah. So okay. So right. Okay. So here's what's happening. So one is okay. So one is like so I'm actually use okay. So here's the thing. So when I describe suppose I give you a check matrix, okay, that corresponds to a stabilizer code, okay, and suppose I were to tell you, like, suppose I gave this exercise. Suppose I'm given the exercise that I want to find out what is the stabilizer code associated with this check matrix. I have a d power n minus k degree of freedom in which stabilizer code I get. Okay, so there is an additional n minus k. I mean, so a check matrix identifies a stabilizer code up to a d power n minus k degree of freedom. Now, where does this d power n minus k degree of freedom come from? Well, when I give you a check matrix, what I end up doing is I just give you, I give you the corresponding generators up to a plus minus sign. I have not told you that, oh, the generator occurs with, oh, this is the generator, or whether it's minus of this generator. Okay, so you get a plus, you get you get generators up to plus minus signs. So what you end up getting is you get stabilizer groups. You get one of d power n minus k stabilizer groups. Actually, wait, not just plus minus sign. Sorry, these are you're not dealing with just plus minus one. You're dealing with omega is a d.
Yeah, you get the root of unity, right?
Yeah, you get the dth root of unity. So there are d power n minus k. You get a degree. You get, if you produce a stabilizer group, you get one of d power n minus k. Okay. Now all of these stabilizer codes, they are very similar to each other. Like, they have a lot of the similar properties. For instance, if you're interested in error correction, with respect to error correction, like the distance scaling or all of that stuff, they're very similar. Okay, what is the fault tolerant design that you need to use for the stabilizer code? Blah blah blah. Everything's the same. Okay. It's just that there are all these different stabilizer codes. They're all sort of orthogonal to each other. Okay, and so when I'm counting stabilizer codes by taking the ratio of the symplectic group by the subgroup, I am not making any distinction between these d power n minus k stabilizer subspaces. I'm just counting them as the same category because, but
Right.
but when I'm actually interested in the subspaces, when I'm interested in singling out one particular subspace, then I need to also factor in this d power n minus k factor. So
Right.
that is what you see, I think, in stabilizer code spaces amounts to me factoring in this additional d power n minus k additional um, factor. And then in that case, when I set k is equal to 0, in that particular situation, when I set k is equal to 0, then I get the
The
all
number.
possible stabilizer state.
Yeah. Yeah, if I understand correctly, I believe that changing the sign or the phase of the generator in this way is equivalent to just keeping the same stabilizer group, and then but instead of picking the +1 eigenstate, you pick like eigenspace with the different eigenvalues.
Yeah, precisely. Yes, that is precisely what's happening. Yeah.
Right? And I have another or a few questions. So in your critical formula that you use to decompose the group T into 4 elements.
Okay. Shall I go to that particular slide?
Actually, okay, maybe I have several questions of this kind. It's like, why does this work? Where what motivates this? But maybe more importantly, yeah, maybe I should ask the more important one for the sake of interest of time. So, uh, so maybe first when you define the MS matrix as a symplectic matrix where H is embedded in there. Okay. So why? Yeah, like
Why did I do that?
yeah. So was it some technique that someone did before, or you just stumble on it for some reason?
So here's the thing. Actually, no. So this technique is something that no, you find a partial. You find that somebody else has partially. I mean, like some other people have partially done this technique before. Actually, a
Mm.
very okay. So if you were to go to chapter number 10 in Nielsen and Chuang, quantum computing, and actually that's a standard book. What's the name? Okay, whatever. It's quantum computing and information, or the other way around, right? So if you were to go to chapter 10, that's on error correction.
Uh-huh.
So their description of like first you associate a stabilizer code to a check matrix, okay, and then
Mhm.
look, you're not only interested in the stabilizer code, you're also interested in. I mean, so you're not only interested, yeah, you're also interested in, let's say, the logical Pauli operators that you can perform on the stabilizer code. But now logical Pauli operators, they are also Paulis. They occur in the Pauli group. They're just identified with respect to the stabilizer code as being logical Paulis. So what is their role, and how does their role come about? Like, can you identify certain end-to-end tuples in the phase space description that correspond to these logical operators? The answer is yes. And where do they occur? Well, they are, so the logical Pauli operators, they would comprise of the columns in this Lx and Lz.
Mm.
Okay, so that is given in Nielsen and Chuang, and not only that, they also actually obtain some sort of a standard form for this Lx and Lz as well. Okay, now what they don't do is also introduce this column E. So
Mm.
I just out of curiosity, I just decided, okay, fine, for the heck of it, I don't like the fact that I'm dealing with a matrix which is some weird size of 2n rows and n plus k columns. I want something that is a full 2n by 2n matrix. And for the heck of it, let me also just try to see if it's a symplectic matrix, and it turned out that is
Yeah,
what sort of got me started. So
yeah. It just surprises me that it is a symplectic matrix. Or should I be surprised? Or
I would feel like saying the answer is no. I mean, you should. I mean, they're actually. So if you, the point is that, if you were like, so if you constrain yourself to think along the direction that, like, first I have only, let's say, k. I'm interested, let's say, in a k-dimensional stabilizer, sorry, a k-qudit stabilizer code. The point is, like, you can always go from a k qudit stabilizer code to a k plus one qudit stabilizer code. Okay, then k plus 2, then k plus 3, so on and so forth. Or you can even shrink it down. You go from k to k minus 1, so on and so forth. How does this matrix, if you're interested, let's say, in just this matrix, in the components of the matrix Lx, H, and Lz, the matrix that you find in this book, Nielsen and Chuang. If you're only interested in that matrix, but if you then vary the value of k, make it larger, make it smaller, how does the resultant matrix, how do they change? What you find is that in the limit of the largest possible values of k or the smallest possible values of k, you end up getting symplectic matrices. So, like, if you incorporate this perspective, you realize that it is kind of natural for you to think of extending the matrix into a symplectic matrix if you were to take this factor into your perspective.
That's interesting. Yeah, thank you. Seems like there's no more question. Well, actually, I have some question related to the stuff I'm doing and my student is doing, but I can catch you later, I think.
Sure, no problem.
Yeah, a bit
I'm always
out.
happy to answer your questions. Yeah.
Yeah. So I guess that would conclude our colloquium today. Yeah. So like I guess let's thanks the speaker Tanmay.
Thanks for having me.
Yeah, that's all I think. So I guess we see you on the backstage.